Here, we're continuing on with the idea of confidence intervals as a method of statistical inference. We're going to use a sample to make an assertion about the population. However, this time we're going to use our calculator to find our confidence interval, and it'll save us a little bit of time. We can see some information, but there is some other information that we have to check first. So if you want to calculate a confidence interval on your calculator, you need to go to the right spot. So the first thing to do is you hit the stat button. You scroll to tests. You can scroll to the right or you can scroll to the left and it'll put you right over tests. And you want to scroll down to 1 prop z int. And this is A on the side. It's way down the list. It's past the numbers, but it's letter A, 1 prop z int. We've got one proportion, and we're going to use the z interval. Remember, z-scores are associated with a normal curve. That's what we're using. We're checking the central limit theorem. And then when you select that, X is the number of successes, the number of people that said yes to your question. N is your sample size. And C level is your given confidence level as a decimal. So example 1 here, we'll find a confidence interval and we'll use our calculator to get that interval. There are a few things we're going to have to do that are missing though. It says in a recent sample of 200 Middle Eastern women, 108 said they used makeup to lighten their complexions. Construct a 99% confidence interval for the population proportion P of Middle Eastern women who use makeup to lighten their complexions. Now, for my particular class, every time you calculate a confidence interval, you're going to need to check the central limit theorem because all of our ideas are going to be based off of the normal distribution. It isn't saying anything in this problem about using a normal distribution. So we need to show that we can use the normal distribution. We have approximate normality here. I can say it's random. That condition is met because we have a random sample of 200 Middle Eastern women. My success number would be the number of women who said yes. That will be the 108. The success number is normally given in the problem. It's over 10, so it's met. My failure number would be, 92. It's over 10, so it's met. My success number and my failure number have to add to be the sample size of 200. What this means is that my sampling distribution, if I were to take sample after sample after sample, it would follow an approximately normal distribution. P would be somewhere in the middle, but I don't know what P is, so I've got to use my sample, my p hat, to sort of estimate this. After the central limit theorem is met, I can just plug in my values to get my confidence interval because that's what I'm asked to do. So X is my number of successes, that's 108. N is not the failures, N is the sample size, it's 200. And we want a 99% confidence interval, so I'm going to change this to 0.99. And then I just hit calculate. Up at the very top, I have my confidence interval. I'll use CI to abbreviate confidence interval. It is 0.449, comma, 0.631. Percentage, you can think about that as 44.9% to 63.1%. So this tells me that I'm 99% confident. I'm very confident that if somehow I could talk to every single Middle Eastern woman, somewhere between 44.9% and 63.1% would say, yes, I use makeup to lighten my complexion. I do have some more information given here. I have that p hat is 0.54. So from my sample, 54% of these women said they use makeup to lighten their complexion. Our boundaries go a little bit lower, down to 44.9%, a little bit higher, up to 63.1%, because we know samples are going to vary from the population. N is my sample size. I already knew that. But note, one thing missing is my margin of error. And it's very convenient to use the calculator to find this confidence interval. It's a lot quicker than the steps that we saw in the previous video. However, the margin of error isn't given here. So you could use the formula for a 99% confidence level. You could go back to your table and you would see that the z-critical value is about 2.57. Square root of p hat is 0.54. 1 minus 0.54 all over 200. Or you could use a little shortcut. If you take p hat and subtract the first number in your confidence interval, that will also give you your margin of error. Because to get your confidence interval, you just took your p hat and you subtracted that error to get the first number, and you added that error to get that second number. So just subtract these first two, 0.54 minus 0.449, and that gives me 0.091. Just to compare, 2.57 square root of 0.54 parentheses 1 minus 0.54. Close those up and divide by the sample size, and we get 0.0905, which would round to 0.091. So we get the same margin of error. In addition, you're going to be asked to interpret your confidence intervals in a formal way. What do they mean? So we can think about it with this phrase. We just sort of fill in the blanks. We are 99% confident. That's our first blank. Or we're 95% confident, or we're 90% confident. We fill in that given confidence level. That the true population proportion, we're using our sample to make an assertion about the population proportion of all blank. Well, what group are we talking about? Are we talking about college students that believe in aliens? Are we talking about Middle Eastern women who use makeup to lighten their complexions? Whatever we're talking about goes in that blank, and it's between your two bounds of your confidence interval. So to interpret the confidence interval constructed in example 1, I would just say, in this case, we are 99% confident that the true population proportion of all Middle Eastern women who use makeup to lighten their complexion is between, and then my two numbers were 44.9% and 63.1%. So we're 99% confident that the true population proportion of all Middle Eastern women who use makeup to lighten their complexions is between 44.9% and 63.1%. I'm not 100% sure about this, but I'm 99% sure based off of the statistical methods that we use. There's a 1% chance that we're off. Just a quick note to wrap up this video, higher degrees of certainty lead to wider confidence intervals. The sample size must be increased in order to have a narrower confidence interval with the same degree of certainty. So what this is getting at originally, higher degrees of certainty lead to wider confidence intervals. We just saw that a 99% confidence interval was 44.9% to 63.1%. If instead I had a 90% confidence interval, you recalculate this going to stat tests, letter A. We have the same situation, but let me bump this down to 0.90. If I calculate this, it's 48.2% to 59.8%. So this is a narrower confidence interval. The 99% has a range of 44 to 63%. That's about 19% gap. The 90% confidence interval goes from 48.2% to 59.8%. So it's much narrower. The gap between these two numbers, between 48% and 59%, you're looking at about 11 or 12% gap. So it's much narrower. That means it's more precise, but we're less confident in our answer. So here we're a lot more confident that we've got the correct population proportion somewhere in here, but it's such a wide range of values here. Here, it's more precise, it's more zeroed in, but I'm less confident in my answer. In order to improve your statistical study, the sample size must be increased. Increase the sample size in order to have a narrower confidence interval. This will allow you to be just as confident and more precise. For example, if I recalculate this with a sample that's 10 times as large, so let's say this is 108.80 and this is 2,000. Let me go back to the confidence level. This is 99%. If I calculate this, my new 99% confidence level, or sorry, confidence interval is 0.511 or 51.1%, 0.569 or 56.9%. So note that this is even narrower than both of these, and I'm still very confident. And I did this by increasing my sample size from 200 to 2,000. Increasing the sample size is the best way to improve your statistical study.